So when we start talking about the expected value of xi, I told you the expected value somehow is the mean value of the random variable, right? So we had some random variable xi, like this, and we say the expected value is going to be the mean value, okay? The mean temperature, the mean pressure. So let's prove it, okay? Let's prove it. That is called the law of large numbers, okay? Law of large numbers. This is just the theorem to prove that the expected value is actually the mean value. Okay? There are two versions. Well, yeah, there are two big versions of the law of large numbers, the weak one and the strong one. So by now we need the weak one. The weak law of large numbers. The weak law of large numbers, we prove it in 2 minutes. The strong law of large numbers, we prove it in 2 lectures. Okay? So that's the difference. So why is it called weak? Next semester you will know the answer. Okay, I don't want to explain that right now. So look, we need a sequence of random variables. So we have xi1, xi2, xin. Right? So we have a sequence of independent, identically distributed random variables. Okay, we have a sequence xi1, xi2, xin of independent, identically distributed random variables. Let me write that the expected value of xi1 equals a, okay, and the variance of xi1 equals sigma squared, and this is finite, okay? So we need the expected value and the variance to be a number, a given number, finite.
Independent, identically what?
Distributed. So we have that these random variables have finite expected value and variance. Then we can prove that for any epsilon greater than 0, the probability that, okay, let me write here also that Sn is equal to the sum of the first n random variables. Okay, Sn is the sum from xi1 to xin. Then what I want to find right here is, I want to find the probability that the mean value, so how far is the mean value from the expected value? So the probability that the mean value, which is Sn divided by n, this is the mean value, the sum divided by n, right? Minus the expected value, which is a. Yes? I want to find the probability that this difference is greater than epsilon. And I'm going to prove that if n tends to plus infinity, then this tends to 0. And that's what we call the weak law of large numbers. Okay, so that the difference between the mean value and the expected value, if n tends to plus infinity, well, tends to 0. So here, we always have this, that n tends to plus infinity, right? That's why probability works, but still, all of this works whenever n tends to plus infinity, which is impossible to have. Okay, so if n is huge, yes, we can apply these theorems, but still we can have some mistake. All right? So always n tends to plus infinity.
Could you explain it again, please? Well, Sn over n minus a, what is inequality?
Well, here we have the mean value, the average value. We sum up everything and we divide it by n. Yeah. And then we have minus the expected value. So we want to see this difference, right? So the mean value and the expected value. What is the probability that this difference is greater than some epsilon? Okay. Where epsilon is any number greater than 0. It can be 5 or it can be 0.00001, right? So any epsilon greater than 0. So maybe in books you will find this, Sn divided by n, and here you will have P and here A. This is the same. okay? And this is the reason why this is called the weak law of large numbers, because of how we write it here. So so there are different convergence. So look, here we have some random variable here. Sn divided by n is a random variable. This random variable converges to this constant. But there are 4 different types of convergence of random variables. This one is called convergence probability or weak convergence. That's why it's called the weak law of large numbers. There are a strong convergence, and in that case, we have a strong law of large numbers, right? Okay, so let's prove it. Proof is very simple. And so we have this. We need to prove that this tends to 0. So let me multiply everything by n. So what do we get? We get the probability that the absolute value of Sn minus Na is greater than n epsilon. Right? Now, what is Na? Well, in respective to Sn. Yes, so Na is n times the expected value of Xi1. So Sn is the expected value of Sn. Yes? So what inequality can we apply? The Chebyshev inequality, right? Well, we don't have it here anymore, but we have Xi minus the expected value of Xi greater than A. So
explain why it's expected value of Sn.
So expected value of Sn is expected value of Xi1 plus Xin. So n times A.
Okay. Oh, they all have the same expected value.
Yes, because they have the same distribution. That's why here I can write only Xi1. That's enough to know that they all have the same. So that the expected value is A for everyone. Now, by Chebyshev inequality, this is less than what? The variance of Sn divided by n squared epsilon squared. Right? Now, what is the variance of Sn equal to? Yeah, well, that's the formula, but we know that Sn is this sum. It's the sum of the variances, and that's it. Is it enough? So formally, we would need 2 times the covariance, but we know that they're independent. So the covariance is equal to 0, right? So this will be just, let me write it, n times sigma squared divided by n squared epsilon squared. So n times the variance of Xi. All right? Because they are independent. Only because of that. If they were not independent, this is not true. Now we can cancel n with this square. We have sigma squared divided by epsilon squared, 1 divided by n. This is a constant right here. So this tends to 0 as n tends to plus infinity. That's it. Very simple. So a very simple inequality gives us already something as important as the weak law of large numbers. Okay. Well, we cancel n, right? So we have 1 divided by n. How did we get? Well, the variance of the sum is the sum of the variances. Because they are independent and they all have the same variance. So this will be n times sigma squared. Yeah? Any questions? Very simple.
Could you explain this part of like less than the variance of Sn of n squared by
This?
yeah.
This
What
is
do you-
Chebyshev inequality.
Okay, so you did it from the last part.
Yeah, we apply. So let me write here, by the way. Yes. Why Chebyshev inequality? And these weak law of large numbers, Chebyshev form. So there's a different weak law of large numbers called in Hinchin's form. Hinchin, also Russian. The difference is that you maybe in that case the variance can be plus infinity, but the proof takes one lecture. So yeah, that's the difference. Okay. So if you change one condition, you have to change completely the proof, right? Well, this is the next question. Yes. So look, now in the proof, what we need. Okay. So everything that is written right here, we use it. If we don't use it in the proof, then we don't have to write it in the condition. Yes. So why do we need them to be independent? Right here. Yes. But actually, they don't have to be independent. Is it enough that they have the covariance equal to 0? So they can be uncorrelated, so that the covariance is equal to 0. We know that if they are independent, then the covariance will be 0. But if the covariance is 0, they don't have to be independent. So saying that the covariance is 0 is more general than saying that they are independent. Okay, we cover more random variables if we say that the covariance is equal to 0. So this is the first condition that we can change. So let me write like a general, more general form of weak law of large numbers. So the first thing, so we have this sequence. And they don't have to be independent. They have to be uncorrelated. So that for every I different from j, the covariance between psi I and psi j is equal to 0. So this is the first condition that we can change. They don't have to be independent. Now, here we have that they have the same distribution. Where did we use that they have the same distribution? Where? Well, here, yes. First here, and here. Yes. So we can, instead of writing an A, I can write just the expected value of Sn. Okay. And instead of writing, so instead of having that the variance is equal to n times sigma squared, all that I need here is not an equality. I need a bound, an upper bound. So I can write that for every I, the variance of psi I, so that there exists a constant C, such that for every I, the variance of psi I is bounded by C. So the variance of every random variable is bounded by some number C. So here I will have less or equal than n times C. What else? Here I have this, look, I have this n squared, and then I need here n for sure because I need to cancel this n. Yes? I need to cancel this n. So I need here n. But then after that, I'm left with n. But if I have here not n, but I have the square root of n, then I still have that this tends to plus infinity. Or if I don't have here n, but I have I don't know, something smaller, ln of n, this is still tends to plus infinity. So all that I need is some function that increases and tends to plus infinity. So I can write it like this. So we have that. We have a sequence of random variables such that they are uncorrelated, and there exists some C, some number, and the variance is bounded by C. Then for any sequence omega n that tends to plus infinity, and for every epsilon greater than 0, we have that the probability that the absolute value of Sn minus the expected value of Sn is greater or equal. And now I don't have to write here n, because here, since I need n here, then I can write here the square root of n multiplied by omega n in epsilon. This tends to 0.
But having n squared is also not a problem.
Yeah, so we just need some epsilon, something like that. Okay. So this is enough, and the proof is exactly the same. But this is way better. Okay, so we change many conditions, we make them more general. Any questions?
Could you go over that again, please? Explain this part.
So
No, we are since the part that you said that we're bounding it by a constant. Yeah.
So next, yeah, yes.
Yeah. Next.
So look,
for
for every such function that tends to plus infinity, so this function will be right here.
Okay.
So this is still tends to 0.
Okay.
This square root of n becomes n, so we can cancel this n. And yeah, that's it. So here I write the expected value of Sn because now they do have different distributions. So the expected value is not n times a. The expected value is, I don't know, the sum of the expected values. Okay. Any questions? So again, the idea is to prove this again in October, but without having this. So we will have only, I mean, this can be plus infinity. Okay, for that we need a lot of material, a lot of tools that we don't have right now. Okay. Now, there's one important implication of this inequality, of this theorem, sorry. And that's proven that actually, so look, what is probability? We said probability is the measure. Right? Probability is measure. So we have defined probability as, for example, in the classical case, in the classical model, we had that the probability was the cardinality of a set divided by the cardinality of the sample space. Yes? Probability of A was the cardinality of A divided by the cardinality of omega. And we have used only this. Now, why probability is frequency? We haven't said that. I mean, I said that at the beginning, that probability was the general, so probability in general represents frequency of something happening, right? We don't see that here. So why probability is actually frequency? We can see it from here, look. So consider the following sequence. So we have the xi1, xi2, xi(n). They have Bernoulli distribution with parameter p. So xi has Bernoulli distribution with parameter p. So we have 1 with probability p, 0 with probability 1 minus p. Okay? So by this, we'll have that the probability that the mean value of the number of successes that we have minus the expected value of psi. What is the expected value of psi? P. The probability that this is greater than epsilon tends to 0. So what is this? This mean value is if you flip a coin 1 million times, right? Then how many times? So what is the rate of times that you get heads? So here we have the number of successes divided by the number of trials. So this is frequency. So Sn divided by n is the frequency of the number of times that a success happened, right? So how many times divided by n we have a success? And we can see that the probability that this frequency is different from p, from the probability of success, tends to 0. So here we can see that probability is actually frequency. Okay, sometimes this is called the Bernoulli theorem or something like that. This is not a theorem, it's a sequence from this. Okay. Now we can understand that we define probability as a measure. We define probability as the relation of the cardinality of a set divided by the cardinality of a different set. But we can see, so we have obtained that actually probability is frequency. Okay? Is that clear? All right. Okay, let's take a break for 2 minutes.